Welcome back to yet another video on probability. Right, we have already finished classical probability, and then we have also seen certain examples. And we have seen what do you mean by uh, empirical probability, right? And what are the limitations? All those things. Let's look at one small example before we go to axiomatic probability. Let us quickly this idea. So let's look at this example. So here's the problem. We need to find the probability that in a random arrangement of the letters of the word examination, all vowels comes together. Okay, so to solve this problem, we should know what are vowels, right? So if I write the vowels, vowel starts from A, E, I, O, U, right? These are the five vowels, and rest everything is called as consonants, right? That's a bit of English. So if I look at this word examination, let's look at how many vowels are together. So there's one E, right? Then two A's, right? Is it right? Two A's are there. Then two I's, right? One O, right? So that means altogether there are six vowels, right? Isn't it? Right. So first of all, how many words can I form? So there are let's write down. There are altogether. How many alphabets are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 alphabets, right? 11 alphabets are there, right? Together 11 alphabets are there. So in which one occurrence of E is there. A occurs twice, I occurs twice, and O occurs just once, isn't it? So what I want to do is how first of all, how many words can I form? The total words can be formed within this. The total number of words that can be formed using the letters of examination are how many words I can form? It's together it's 11 factorial, right? Into 2 factorial into 2 factorial, right? That comes out to be all together. You can check that out. That as okay. So this would be equal. It comes out to be 9979200. Check that if you have a calculator. You can always go back and check how many words can be formed, right? It's not so difficult. Uh, now, if all the vowels are supposed to come together, now to find the number of words in which all vowels comes together, right? We consider A, A, I, E, O as one letter. So what happens is if we need to consider this six letters because all are vowels, right? This has the one letter. So altogether, how many letters do I have? I have one, two, three, four, five, n plus one. So there are First of all, how many words I can get if I use the letters of so how many ways I can permit this? There are 6 factorial, right? Uh, permute. What I can say. Um, there are six factorial ways we can permute these letters. So we can permutations permutations of permutation. There are 6 factorial ways we can permute the above 6 letters, right? And they would be permitting alongside them, right? So the total word, therefore, the total words in which vowels occurs together would be equal to 6 factorial, first of all, right? Multiplied by its 1, 4, 5, 6. 6 factorial over 2 factorial into, if I'm correct, that comes out to be, um, yeah, is there's a mistake somewhere? This must be 6 factorial, right? Yeah, because the total words are 11. If I take 6, what remains is 5. 5 plus 1 is 6. Yeah. So 6 factorial, right? 6 factorial, if I look at multiplied by 6 factorial again, divided by 4, comes out to be 129,600. 129,600, right? So these are the numbers in which vowels will occur together. So the probability of the event that all vowels occur together is equal to the total number of possibilities. It's 99727 over 129,600. Cancel out this, and what remains is can check that out. Probability comes out to be 0.1. Check that out. This is what you get. 0.0 actually. I missed. 0.013 is the answer. Check that out for your uh, yeah. That's what I wanted to discuss. Let's go to something else. So let's look at axiomatic. Nice thing. What are the axioms of probability? Should satisfy. Let's look at this one. Q&A, sample space, S of a random experiment, probability of occurrence of any event A is defined as That um okay, it's defined as a function, by the way. Defined as a function satisfying the following axioms. Let's see what are the axioms it satisfies. So this function p is a probability function, right? It satisfies the following axioms. Axiom it says that probability of any event is a definite non-negative number. That is, probability of any event is bigger than or equal to 0, right? This is called as axiom of non-negativity. Axiom of non-negativity, right? Let's look at axiom number 2. It says that if I look at probability of the sample space, it's 1. Okay, this is called as axiom of certainty, right? Axiom of certainty, right? Where we know that S is a sample space, where I've already written here. Let's look at axiom 3. Okay, what does it say? If A1, A2, A3, so on up till AN and so on is any finite or infinite sequence of disjoint events, disjoint events, right, of the sample space S, of the sample space S, then if I look at probability of all the unions I going from 1 to n AI, right? This is nothing but sum of the probabilities, right? This is nothing but the sum of probabilities. Or if I look at the infinite sequence, you going from 1 to infinity AI, so the summation I going from 1 to infinity PR, right? This is called as axiom of additivity. Axiom of additivity, right? So remark, let's write down. Remark, these definitions is useful even when outcomes are not known to be equally likely. It's not only limited to classical probability, it can be used to other aspects, right? So that's what we have in axiomatic probability. Next up, we would see what addition uh, okay, let's look at addition theorem um, of probability. What it means is if I have two events A and B, um, then probability that A happens or B happens, that means either of them happens, is given by probability of A plus probability of B minus probability of A and B happening together. Right? That's the idea. Okay, proof is not there, so proof is omitted. Problems are not. You have to a lot of right. Some remarks. First of all, remark one. What happens if A and B are mutually exclusive? If A and B are mutually exclusive, that is A intersection B is empty, it would imply that probability of A and B happening together is zero, because they have nothing in common. Therefore, in this case, probability of A union B becomes probability of A plus probability of B. Right. Second remark, what happens to probability of A happening or B happening or C happening? This is equal to probability of A plus probability of B plus probability of C, right? Subtract probability of A happening or B happening, subtract probability of A happening or C happening, subtract probability of B happening or C happening, add it to probability of A intersection B intersection C. That's so, example. Okay, so let's look at this example. We draw a card from a pack of 52 cards. We know that a pack of card has 52 cards. We need to find the probability that the card which is drawn is either a spade or a black card. And second problem is it's either a king or so. Look at this. First of all, as we know, spades are also black cards, right? Just take this here, are also black cards, right? So, what would be first of all, okay, let's look at first of all. So this is what we should spades are also black cards, right? So let A be the probability. Okay, let A be the event. Let A be the event of drawing a card which is a spade, right? Therefore, what happens to probability of A? Probability of A, since there are 13 spades, probability becomes 13 over 52 over which is equal to 1 over 4, right? Let B be the event, right, of drawing a card, right, which is a black card. Therefore, what happens to P of B? Since there are 26 black cards, it becomes 26 over 52, which is equal to 1. These events are not mutually, which are not, these events are not mutually, what I can say, I mean, events are not mutually exclusive because black cards and spades are having common thing in between them, right? So now we need to find what's the probability of their intersection, right? Uh, what would be probability of um, A and B happening together, right? That means it's a what's the probability that the card which I pick is spade and also it's a black, right? Note that there are 13 black cards, right? Which are spade, isn't it? Therefore, what happens is probability of A intersection B. That means probability that it's a spade and also it's a black, right? There'll be 13 over this 1 by 4. Therefore, what happens is probability that A union B rather, sorry, probability that A or B happens is nothing but by formula. This is probability of A plus probability of B minus probability of A intersection B. But this is nothing but 1 over 4 plus this is nothing but half. This is nothing but 1 over 4. So this is exactly half. You can see that whatever card you're choosing, red or black, right? So exactly equal to. Second one, this was the first one. Okay. Second is pretty much kind of easy, right? Let A be the event. You can change the alphabets of choosing a card which is queen or king. Let's use king. Therefore, probability of A becomes 4 over uh, 52, isn't it? Right. And let B be the event of choosing a card which is a queen. Therefore, there are 4 queens, so P of B would also be equal to 4 over 52. Now, if I look at a card which is I mean, king or queen, they don't have either it has to be a king or it has to be a queen. They don't have a king cannot be a queen, queen cannot be a king. Therefore, what happens is probability of A intersection B, they are mutually exclusive, right? Drawing a king and drawing a queen doesn't have anything to do with each other, right? They are independent events. Uh, so therefore, so it's zero, in fact, right? Zero, right? Therefore, what happens is this is zero. I hope. Therefore, what happens is probability of A union B in this case becomes probability of A plus probability of B. That's 8 over. Right? You can see whatever is this because this would be if I do this, this would be 2 over. Right. That's the idea about the problem. I hope this is kind of clear. Let's move on to the next problem. Well, I would kind of give you exercise on this. So you will be able to solve more problems. Try and give you as much as work problems as possible. Okay, so next example. So let's look at this problem. Um, what we have is um, there's a bag um, which contains 100 tickets, so you can consider them as balls. Okay, they're named from 1 to 100. Um, okay, so tickets are numbered from 1 to 100, and you are drawing a ticket at random. You need to find the probability that number on the ticket. What's the probability that the number is a multiple of 2 or a multiple of 3? And second one is what's the probability that it's a multiple of 4 or a multiple of 5? Okay. It's a very simple problem. First of all, you need to remember that bag contains 100 tickets and they have numbers on them, right? Now, let's look at how many multiples of 2 would be there here, okay? So if I look at the ideas, every even number from 1 to 100 is a multiple of 2, right? Multiple of 2 as in 2 should divide that number. So multiple of 2 would be exactly half the numbers from 1 to 100. Like almost, if you look at 100 numbers, then half of them would be even, half of them would be odd, right? So note that the total even numbers, So the all even all I can use this. Note that all the even numbers are multiple of 2. Therefore, probability of A would be exactly equal to how many, as I said, it'll be exactly half of 100, right? 50 over 100 comes out to be, right? What about multiples of 3? Let's count. All the multiples of 3 would be exactly sitting at a difference of 3, and all will be in the table of 3, right? So from 1 to 30, there'll be exactly 10 multiples of 3 because uh, it's all exactly if I add 3 10 times, I get 30, right? So exactly 3, 6, then 9, and so on, right? So from 1 to 30, there are 10 multiples, then 30 to 60, there are 10 multiples, then 60 to 90, there are again 10 multiples, and from 90 to 100, there are 3 multiples. So note that, note that there are 33 multiples, right? Multiples of 3 multiples of 3, as I said. So what happens is probability. So here A be the event of getting a multiple of 2. So let B be the event of getting a multiple of 3, right? This implies that probability of B would be equal to exactly 33 over 100. Now you need to remember that every odd number, every multiple of say 3, it can also be can be a multiple of 2. For example, 6 is a multiple of 2 and 3 both, right? Then 12 is a multiple of 2 and 3 both, right? Then 18 is a multiple of 2 and 3 both, right? So how many such numbers I can find, right? So you need to remember that any multiple of 2 and 3 is also a multiple of 6, kind of their LCM, right? Any multiple of 2 and 3 is also a multiple of their LCM, that is 6, right? So let's write down. Note that, note that any multiple, any number which is a multiple of, any multiple of 2 and 3 both is also a multiple of LCM of 2 and 3. That is, I hope you all know what's LCM, right? Therefore, right, probability of A intersection B, how many multiples of 6 I can have? From 1 to 60, there are 10 multiples, right? Then from 60 to 100, there will be what? 6 multiples, right? So there are total 16 multiples of 6, right? So therefore, probability of A intersection B is 16 by 100, right? Therefore, so therefore, what we have is A union B here. Let's do that. Okay. Therefore, A union B would be nothing but P of A plus P of B, that is half. Uh, or let me keep that as okay. Let me keep that as it is, so that it would be better. It will be 50 by 100 plus 33 by 100 minus 16 over 100. That comes out to be 33 is 17, right? So this would be 67 over. So the probability that it will be either a multiple of 3 or multiple of 2 would be exactly 67 by 100. Now, if I look at the second problem, a multiple of 4 and 5, that's in the same way, right? So let's do the second one. Quickly do this. So second one here, let A be an event of drawing a card which is a multiple of 4. So how many multiples for 4s we have from 1 to 40 we have 10, right? Then 40 to 80 we have another 10, and 80 to 100 we have another 5. So altogether there'll be 25 multiples, right? So therefore what is P of A? P of A would be 25 over 100. Similarly, let B be an event of drawing a card which is a multiple of 5, right? So P of B here, how many uh, multiples of 5 do we have? From 1 to 50 we have 10, and 50 to 100 we have another 10, right? So altogether 20. So this would be 20 over 100, right? I hope this is clear why I'm writing 25. This is 20 favorable to this event, and total number of outcomes is 100, right? And what about A intersection B? Note that, okay, a multiple of 3, sorry, here it's a multiple of 4 and 5 is also a multiple of 20, isn't it? So what happens is, if I look at uh, the very first number, 20, 20 is a multiple of 4 and 5, right? Then what else? 40 is a multiple of 4 and 5, right? Then 60 is a multiple of 4 and 5. So anything which is a multiple of 20 is, anything which is a multiple of 4 and 5 is also a multiple of 20. Therefore, what happens? P of A intersection B would be equal to, how many multiples of 20 do we have? Exactly 5, right? So this would be 5, 20, 40, 60, 80, and 100, right? So therefore, P of A union B in this case would be 20 over 100. Sorry, first of all, it's 25 over 100, right? P of A. So that's 25 over 100 plus 20 over 100 minus 5 over 100. So this comes out to be 40 over, and that's the